I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, thank you for these students and for the weekend. Pray that you'd just guide our thoughts today. Help us to, again, Lord, just to glorify you in what we do, Lord. In your name I pray. Amen. Let's see here. So, today we will continue our discussion of abstract vector spaces. In particular, we're introducing a new concept, namely that of basis and coordinates. So what I'll try to do today is just to give the basic definition, show you how to calculate a few of these things, and then Wednesday I'll actually go through a little bit more of the theory. So start with a definition. This is definition 6.5.1. A basis for a vector space V, all right, over a field F, all right, is an ordered set set of vectors, let's say S, such that two things. Number one, it's a spanning set. So V is the span of S. All right. And two, S is linearly independent. All right. So this is what a basis is. A basis is a linearly independent spanning set for your vector space. All right. So here's a couple of theorems. I'm going to state a theorem which is kind of intuitively obvious, but I'm not going to prove it. If I actually prove this theorem, I think if I remember right, it takes me about a half hour. But it seems simple enough. So here's the theorem. Let V be a vector space over F. All right. And suppose that W is equal to the span of V1 through Vn. All right, so that's going to be a subset of V, all right, period. Here's the punchline. If we have W1, W W sub M is a subset of W, all right, and M is greater than N, then the set W1, W2, well, W1, Wm is linearly fill in the blank. All right. So my point to you is this should be, if you're starting to gain some kind of intuition for what linear independence and linear dependence means, can you complete this sentence for me? What would kind of make sense? So basically the data says you can build this space W using n vectors, right? Then I'm saying this other set containing the W's, the big W, has m vectors, and m is larger than n. Right? Yeah. Linearly dependent. Yes, that is in fact true. The operative idea here is that the basis is essentially a minimal spanning set. All right? It's like the smallest spanning set you can get. Linear independence assures us that minimality, that we can't remove anything from S and still get the same span. Right? This is easy enough to understand, this theorem, but it's much harder to prove. I'm not going to prove it today. But once you know this theorem, which is my 6.5.2, it allows me to state theorem 6.5.3, which I think I will prove. It won't take long. If V is a vector space over a field F, right? And we have V1, Vn is a subset of V, all right? And W1, Wm through Wm are linearly independent, right? With the span of the V's matching the spans of the W's. Then what? What should the punchline here be? You're starting to gain some intuition. Maybe you could tell me what the answer ought to be. We have both these sets. They're both linearly independent. They both reach the same spanning set, right? They both cover the same sort of line or plane or volume, whatever. What should we be able to say? How should M and N relate? Yeah, they should be equal, right? And that's the theorem. Now, if we know theorem 6.5.3, which is 5.2 rather, which is not easy to prove, it's not that hard to prove this. Let's prove it. So proof. So let's suppose, suppose that V and W are given as in the theorem, and consider M is greater than N, right? If M is greater than N, observe that Wi is an element, where was I? Of the span of V1 through Vn by assumption, right? We're assuming the conditions in the theorem. Right? One of those is that this that the spans are equal, right? So if Wi is Wi in here, right? So you notice that Wi is equal to 1 times Wi, right? So that's in the span of W1 through Wm. The span, of course, always contains the vectors which it's spanning, among other things, right? Like S is a subset of span S. Anyway, so Wi is in that span, right? And that's for what? For each I equals to 1, 2, all the way out to M, right? Hence what? We've got that W1 through Wm is a subset of the span of the V's. Right? But what's that say? We have a subset with more than n vectors inside the span. What does that imply about the set containing the W's? By theorem, this one, that I have improved, 6.5.2, we find what? This set, W1 through Wm, is linearly dependent. But what did we assume about the set containing the W's in the statement of the theorem? We assume that they're linearly independent, right? So garbage in, garbage out. The garbage in here is M greater than N, right? apparently that's an impossibility because it produces a contradiction. So therefore, thus, m is not greater than n. And you can give the same argument with the roles of m and n reversed, right? We can just as well as look at v sub I being in the spans of the w's, and then produce an argument which says that the set containing the v's is linearly dependent, which then would deny the possibility that n is greater than m. So what's left? Similarly, show m is not less than n, right? So apparently m equals to n. All right? So in other words, if there exists a finite linearly independent spanning set for a vector space, well, in this case for a subspace, which I've not even named, right? What's the vector space I'm talking about here? It's not V. This is all taking place inside V. I haven't even labeled the vector space we're describing the basis for. If you wanted to, we could call this span something, I don't know. Let's call it U, right? The point is U has basis, well, it has two different bases, right? It has the V basis. This is a linearly independent spanning set, and it has another basis, W1 through WM, also. And I should really use bases because it's plural. There's two of them, right? These are both bases for U. And what did we just learn? We learned that the number of things in those have to be the same. Okay? So that theorem is important. It allows me to make the next definition. Let me erase those very uninteresting graphs. Right? What is this? Statistics? Economics? Statistics. Ugh. Ugh. We don't need that kind of lying in here. Let's see here. Sorry, definition. If you've got an honest point to make, you don't need statistics, right? Let's see here. Sorry, definition. I'll shut up. Anyway, let V be a vector space over F, all right? If beta is a subset of V, all right, is finite. What's a finite basis? All right. Then we say the dimension of V is equal to the number of elements in beta. Right. More generally, the cardinality of a basis for V is the dimension of V. Right. If it has a finite basis, it's said to be a finite dimensional vector space. For the most part, we study finite dimensional vector spaces in here. All right. So let me just get some examples out here. Well, actually, let me make another definition while we're at it before I even do that. Definition. If, bless you, if V is a vector space, has finite basis, let's say beta, and I'll say V1, V2, Vn. All right, suppose that that's the finite basis for V over F, all right? And if if we have x in V, has x equal to C1 V1 plus C2 V2 plus plus Cn Vn, all right? Right, for some C1, C2, Cn in the field, all right? Then the coordinate vector of x with respect to basis beta is equal to the column vector C1, C2, Cn. So let me just get it out on the table here. Admittedly, logically, I haven't quite paid my dues yet. I should show you that the coordinate vector, if it exists, is unique. You know, I should really prove that this coordinate vector is unique. Coordinate vector of x. This is a column vector. In Fn. So this notation square sub beta means coordinate vector of the vector with respect to the beta basis for us in here. So before I regret my life more, let us pause and prove that the coordinate vector is actually well defined. It should be a single thing, right? How could I prove that the coordinate vector is uniquely specified by the vector in the vector space? Is the coordinate vector a reasonable construction? So what should we do to show it's just one thing? How about this discussion? If beta v1, v2, vn is basis for v over f, all right? And x in V has two coordinate vectors so what would that look like? That would mean that I could write x as, C1 V1 plus C2 V2 plus Cn Vn like that, right? But suppose I could find some other set of numbers. Let's say, for lack of imagination, B1 through Bn. Right? What if I could also write that as B1 V1 plus B2 V2 plus Bn Vn, right? What would I like to do? I'd like to prove that it is inescapable that B1 is B2, that C1 is equal to B1, that C2 is equal to B2, and so forth. I want to prove that the coordinates are uniquely specified by the basis. Right? So the fact that the basis is spanning, what's that mean? That means that I can it doesn't matter which x I pick in the vector space V, right? I can find these constants C1 through Cn, which attain x in the span of the set, right? That's what spanning gets me. What's linear independence get me? Linear independence gets me, among other things, the uniqueness of the coordinate representation. Let me show you how. So all you got to do is take this equation here, and forgive me, I'm pretty much solving one of your homeworks for you here, because one of your homeworks is to prove the equating coefficients property for linear independence, right? Namely that one of the ways you could characterize linear independence for a set of vectors is that it satisfies the equating coefficients property. How do you prove that? It's really not that much to it. So if this is true, then I get what? I get C1 V1 minus B1 V1 plus C2 V2 minus B2 V2 plus Cn Vn minus Bn Vn equal to what? Equal to 0. But then all you got to do is just collect things, right? C1 minus B1 times V1, C2 minus B2 times V2, Cn minus Bn times Vn equal to 0. But what did we assume? This basis is a basis. It is linearly independent. We have set a linear combination set equal to 0. By linear independence, the coefficients must all be what? Yeah, they must all be 0 separately. So like C1 minus B1 equal to 0, C2 minus B2 equal to 0, and on down the line, right? Thus, C1, C2, Cn is in fact equal to B1, B2, Bn, right? And we justifiably use a single notation for both of those. That is the coordinate vector of x with respect to the beta basis. That's what linear independence gets us. It gets us uniqueness of the coordinate vector. Now, devil's in the details here. You do need to pay attention to one of the words I used, which was ordered basis, right? Ordered. All right, so we got everything out on the table now. Let's look at some actual examples. Well, a couple of these examples are kind of meta examples. And just acknowledgement that we've been using these words without meaning, but with the right meaning, nevertheless. So like example 1, you may recall that Rn, right, is the span of E1, E2, En, right? So this beta is the standard basis. That term, standard basis, means what it means. It is a linearly independent spanning set for Rn. So what's the dimension for Rn over the reals? Not complicated, folks, right? This is what? N, right? On the other hand, we've also talked about the fact that you could take, fine. By the way, I could replace this with a field f, right? And I could replace this with Fn. And I like to put, sometimes it's the f dimension of that. I mean, technically I'm talking about real dimension here. When we have a point set, which you could either think of as a complex or a real vector space, you could talk about its complex dimension or its real dimension. They could be different. They're related, but they're different. So Rm by n, right? What's the basis? That's the span of what? We get these Eij's such that 1 is less than or equal to I is less than or equal to m. 1 is less than or equal to j is less than or equal to n. Right? That's our matrices with zeros mostly in just one in one spot. That we can build any matrix from a span of those. It's easy to prove that they're linearly independent. So in fact, those form a span, a basis for n by n. So this is the, if you call that beta, it's the standard. Now, standard basis for Rn by n. Now that's admittedly ambiguous, as I've currently stated it. Why is it ambiguous? By the way, you could replace R with F. You'd have a basis for Fm by n. The reason it's ambiguous is I've not made clear the ordering. Not made clear the ordering of the basis, right? And you could go with different orderings, and those would give you different bases, all right? So let me expand on that in the 2 by 2 case, okay? So like, we could let beta equal to, say, here's what I usually go with. E11, E12, E21, E22, right? So if I look at the matrix A, which has got A, B, C, D, I can rewrite that as A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. Right? Now, hopefully you remember, this is my E11, right? This is my E12. Here's my E21. And here's my E22. This is what I would say the standard lexicographic ordering. I think it's the standard lexicographic ordering. Is that right? Yeah. sort of treating the first number like the first letter, going from 1 to 2. So what does this linear combination show? This shows me the coordinate vector of A with respect to this beta basis is what? What's A sub beta equal to? It's column vector, actually. It's A, B, C, D. There you go. Now, same matrix, if I took the basis gamma to be, say, E12, E11, tell you what, I'll do it in a kind of an orderly way. I could do E11, E21, E12, E22. This is a basis some people might use, right? With respect to that basis, what's the coordinate vector of A with respect to the gamma basis? The ordering matters, you see. So, we could say A is equal to A E11. What's the E12? Plus C E21, rather. E12 was plus B E12 plus, where was I? D E22, yeah? So this would be A, C, B, D, right? So my first choice of basis, right, it converts, in some sense, the matrix, a 2 by 2 matrix into a 4-column vector where we're basically stringing out the rows, right, as a column, row by row. That choice of basis, what does it do? It just strings out the columns as one big column, column by column. That's another popular ordering for the basis for 2 by 2 matrices. Is it written in stone, which is the ordering? Not really. I mean, by default, I'll use the first ordering, the lexicographic ordering. But there really is no, I don't think it really is written in stone. In contrast, there is a standard basis for Rn, right? So that's the one kind of vector space where we have this sort of pre-existing basis that everyone agrees to work with, So a lot of the constructions we do simplify considerably when we work with Rn as compared to other vector spaces. Example 4. If we look at, I sometimes call it P2R. I think the notation I'm starting to like would be R of x, n less than or equal to 2. So in other words, quadratic polynomials. This has basis. What can we choose for basis? How about this? 1x, x squared, right? So what if I wanted to find the coordinates of some, let's look at the vector. What's an interesting vector? How about consider vector v equal to x plus 1 quantity squared, right? That's in P2. It's a quadratic polynomial. What's its coordinate? What's its coordinate vector? How would you figure that one out? So I mean, not rocket surgery here. Rocket surgery? It's a new one. Let's see here. X squared plus 2x plus 1, right? I assume you can do algebra. So what's the coordinate vector with respect to the beta basis? What's v sub beta here? Let me just one more step. Let me rewrite it. This is 1 times 1 plus 2 times x plus 1 times x squared. See, I have to put it in order. It's an ordered basis, ordered set. 1 copy of 1, 2 copies of x, 1 copy of x squared. So the coordinate vector, that's not a TIE fighter or whatever, but this is 1, 2, 1. There you go. So finding coordinates can be as easy as just understanding the definition, right? Take a break here from coordinate calculation to talk a little bit more about cardinality and some kind of more exotic examples in some regard. So we talked about, so here's some infinite dimensional examples. So for v equals to r join x, in other words, the polynomials, this is, polynomials in x, right? This has beta equal to 1x, x squared, dot as basis, right? We proved last time, in fact, that that's a linearly independent set, remember, with calculus? And the fact that that's a span of the set of polynomials, that's pretty much the definition of polynomials, right? So that's definitely a basis for polynomials. And how many vectors are in there, in this beta? Is it finite? Certainly not, right? So polynomials give us a nice example of an infinite dimensional vector space. And its dimension is the cardinality of the natural numbers, right? It's countably infinite. Another example, of course, would be functions, right? From the reals to the reals, right? Function space. How many different functions are there from the reals to the reals? Linearly independent functions. Well, here's a hint. The polynomials are in there, right? So here's one of those theorems that's not too hard to prove. If you have a vector space and it contains a subspace which is infinite dimensional, it's infinite dimensional. You can't somehow have a subspace which is infinite dimensional, but then somehow when you get to the total space, it becomes finite dimensional. Like that does not happen for vector spaces. So anyway, this function space is infinite dimensional. How about all of your favorite other sets of functions, pretty much? Well, not every, though. I mean, certainly the set of continuous functions, the set of once differentiable functions, twice differentiable functions, thrice differentiable functions, the smooth functions, the analytic functions, all those fun ones we talked about. Those are all infinite dimensional because there's an unending list of linearly independent examples of those, right? But there was one function space which was not infinite dimensional, right? I mean, you can have subspaces of an infinite dimensional space that are finite dimensional. For example, the solution space of y prime prime plus y equals to 0, this thing, all right, is a subspace of the set of smooth functions on the reals. In fact, and this is, again, this is outside the scope of this course to prove this, but in differential equations, you learn that the solution space of the differential equation y prime prime plus y equals to 0 is nothing more than c1 cosine t plus c2 sine t, such that c1 and c2 are real numbers. So that's actually what that solution space looks like. You can prove that cosine and sine are linearly independent as functions, so that's actually a two-dimensional subspace of that infinite dimensional space of smooth functions. And much of what we know and love about differential equations follows from looking at solution sets. Solution sets are very nice. Solution sets to nth order differential equations are actually finite dimensional subspaces of an infinite dimensional vector space. And because we have that like finite dimensional subspace, we can play all kinds of finite dimensional games with these Wronskians and other things. All right, some of you will take differential equations, learn more about that. Great. Others of you won't. sorry about that. I feel like you've been cheated, but there's nothing I can do about it. Let's see here. I have no such power. So, remain ignorant. You have my blessing. No, you do not have my blessing, but you have my permission. Actually, you don't need my permission to stay ignorant. That's just something you can do. Or don't be ignorant. I don't know. Anyway, we're all so much less stressed now that the Olympics are over and we can finally focus on our studying again, right? I know, like, it's been eating up a lot of your time. What's going to happen with the curling, you know? I watched a solid half hour of that, and I saw the most incredible curling move ever. And I could appreciate that most of the one color was eliminated and just the other color remained after that incredible move, but I still have no earthly idea how it's scored or works. I should just go to Wikipedia and read the article and then watch, right? I mean, just watching, it didn't work for me. I don't know about you guys, but I know you're too wrapped up in the figure skating, I know, but I'm sorry. Olympics. All right. Another example. So I want to do some more calculational examples here. Oh. Subspaces. Subspaces of a matrix. This I have neglected to tell you yet, but I should. So now that we have all of our favorite bells and whistles to play with, we can now return to the question of taking a matrix and ripping it apart into its pieces and understanding it in terms of its fundamental subspaces. There are 3 fundamental subspaces attached to a matrix. So let's suppose A is an M by N matrix over some field, right? So definition, the column space of A is the span of column, let's see here, how's it go? Column J of A such that J equals to what? How many columns does an M by N matrix have? 1, 2. Oh no, I guess we're going to forever remain mired in mystery. How many columns are there in an M by N matrix? No one has an answer. Come on, it's the low-hanging fruit. Pick it. Someone pick it. M. Okay, very good. Oh, N. And this one was M. That's what you're telling me, right? Yes. You're waiting until I had both on the board so you couldn't be wrong. I appreciate that and admire it. That maybe was not what you're doing. You're answering the most recently asked question. I understand. Let us not speculate as to your motives. Anyway, I'm just glad to have received a letter. So, and then of course there's the dreaded null space of A, which is not a span, but it is defined to be X in Fn, such that Ax is equal to 0. Null space, also known as the solution set to the homogeneous equation. I say these are fundamental subspaces connected with a given matrix. Do you see why? I mean, are they subspaces? Am I right? So how do you prove these are subspaces? Since they're what? How do you prove that these are subspaces? If you don't own this fact, you're leaving yourself wide open for wasting inordinate amounts of time on the next test. You must internalize this fact. A span is a subspace. This is one of our theorems, right? So the fact that they are defined as the span of vectors means they're subspaces, resting on the observation that linear combinations of linear combinations are linear combinations. So it passes the subspace test. The fact that the null space is a subspace, well, that's simple, right? First of all, to prove that this is a subspace, here's the proof, right? Notice that A times 0 is equal to 0. Therefore, 0 is in the null space of A. Let X and Y be in the null space of A. and let C be a scalar in the field. Then if we look at A times Cx plus y, that's C times Ax plus Ay, which is what? C times 0 plus 0, otherwise known as 0. What does that show me? That shows me that Cx plus y is, again, killed by A. It is in the null space, right? Thus, Cx and also x plus y is in the null space of A, and so the null space of A is a subspace of Fn by the subspace test, right? So, natural question then is, how do you find a basis for the column space, right? How do you find a basis for the row space? How do you find a basis for the null space of a given matrix? These are pretty typical questions that we ask. There's some of those in your homework. What would it mean then? How would you find a basis for the column space? What would be required for a given matrix? It should be a what? A linearly independent spanning set. So if you guys understand the column correspondence property, what should you probably use as a basis for the column space? Ooh, I forgot what number I'm on. 5? Is it 5? I don't know. You can find a number. So let's think about A being, I don't know, 1, 2, 3, 4. Look good? And then 2, 4, 6, 8. This is kind of a silly matrix. Let's find a basis for the row, column, and null space of A. So this, of course, we can do what? Row 2 minus 2 row 1. What's that get us to? Huh. Well, there you go. That is, in fact, the reduced row echelon form of A. Sorry, it's kind of an anticlimactic calculation there, but there it is. So the column space, what can you observe about it? Every column is what? It's just a multiple of what? The first column, right? Is the, so column space of A would be the span of 1, 2. Right. How about the row space of A? Well, row 2 is just twice row 1, right? So you could pick either one for a basis because you can get the other from the remaining one, right? So the row space, the row 1, 2, 3, 4 works nicely for the basis. These are kind of boring. These, both of the row space and the column space are both one-dimensional in this example. But how about the null space? What's the null space look like? It's the thing you guys tend to have more trouble with until you master it, in which case, after you master it, it's kind of like not a big deal. But so we're looking for x, such that ax equal to 0, right? So that is what? That is actually, looking up here, right? This tells me that x1 is minus 2x2 minus 3x3 minus 4x4 for that equation, right? So I just plug that down in here. I've got minus 2x2 minus 3x3 minus 4x4. And then I got my x2, I got my x3, I got my x4, such that x2, x3, and x4 are free. And I'm assuming we're working over the, I chose my field to be the reals because, well, it just makes you guys feel more at home, right? You guys like to keep it real. Let's see here. Oh, I'm sorry. That joke is dated. But it just keeps happening. I can't help it. So, you look at this. What you got? You got yourself an x2 minus 2, 1, 0, 0, plus x3 minus 3, 0, 1, 0, plus x4, which is minus 4, 0, 0, 1, such that, again, x2, x3, x4 are free, real parameters. So it should be apparent to you that, in fact, the null space is the span of these guys, minus 2, 1, 0, 0, minus 3, 0, 1, 0, minus 4, 0, 0, 1. And this thing, without the span, is the basis for the null space of A. The null space of A is, in fact, three-dimensional. It's the one that you can't just cherry pick from the columns and rows of A. I mean, the row space of A and the column space of A have to be formed from rows and columns of A, at least in principle. But on the other hand, the null space of A, is this anywhere in A? You look at these. Are these in A? Well, no. Do they have a relation to A? Can you tell me something about the relation between the null space and A? Maybe something about dot products. What does it mean for AX to equal to 0? We have what? We've got row 1 of A stacked with row 2 of A times x equal to 0, right? So that's really nothing more than row 1 of A dot x equal to 0 and row 2 of A dot x equal to 0 if we break that down into two equations, two dot products. So yeah, the solutions to the null space should include vectors which are perpendicular to the rows of A. It's easy to check what those are, right? The dot product of minus 2, 1, 0, and that guy, and that, they're all perpendicular to 1, 2, 3, 4, and by extension, 2, 4, 6, 8. So there's something neat about the null space as it relates to questions about perpendicularity of a given set of vectors, right? Something to store away in your memory for later. So next time, I will show you exciting things like how to actually calculate coordinates for things which are not obvious. I mean, these questions you already have tools to solve. What we have not discussed yet is, given a non-standard basis of Rn, how do you find the coordinates with respect to that for a given vector? So I'll describe that next time, as well as some of the deeper theory in here. So, thanks, guys. So should I keep wearing this shirt? What's the consensus? Should this be my new uniform? All right. Isaac will be happy. I'm wearing this for Isaac. It's his birthday party. We gave these out as party favors. So it's known as a tie-tie. I don't know why it's a double tie, but I think of it like an exclamation point upside down. It's understated,